Good afternoon, gentle readers. This day is May 12, 2024. It is about 1:55, 1:56 in the afternoon. And what I hope to do today was to illustrate some more of the ideas of moment and motion. So today, in moment and motion, I don't really have much, because what's developed so far is kind of this entire consideration of the V viva, and as vis-a-vis the V motrix, the motive force and the active force, in the definitions of the theory of mechanics, classical mechanics, and modern classical mechanics, with regards to the statics and dynamics and the ideas of the most usual sort of least action expressed as a sum of histories, sum of potentials theory, and with regards to our canon and our dogma and doctrine of the scientific method and our historiography of all the accounts that I can possibly scrape together from these fragments of papyri and clay tablets from the ancient times of the ancient Sumerians to the ancient Greeks, and you know, as with regards to what influences they may have garnered from the Nubians or the Proto-Egyptians, or anything with regards to the Vedas and the Rig Veda, and what we have as historical and prehistorical with regards to theory. And so it is so arrived at that a central figure in that is Aristotle. And well, because he's a great cataloger of all the things that there were at the time. And kind of like if you consider that Euclid, the great geometer, was a panel, and so Euclid was a man, but also that his works were kind of apocryphally all written variously and assembled, compiled to make the books of Euclid's Elements. And then there's something like Aristotle and his prior and posterior analytics and physics and metaphysics. And with regards to then the more ancient Greeks, which I call the Eleatics of Parmenides and Heraclitus and Zeno. And then was with regards to Archimedes and Pythagoras, and then to, well, I don't have much to say about Socrates, but Plato and then Aristotle. So then those are, of course, recounted by everybody since antiquity, like Augustine of Hippo, I suppose it is. There's Leucippus, Simplicius, Lucretius, Romans, from various times in the beginning and end of the Roman Empire, circa 50 AD to circa 550 BC. And then as with regards to Averroes and the Enlightenment and the Muslim world, and then back into then the later age of the scholasticism, the Mertonians in Oxford quite later, but after Spinoza and Scotus and the Scotists and this and that, up into the great age of the Enlightenment, and reaching up to past the Mertonian school, and 100 years later to Galileo, and 100 years later to Newton, and Maclaurin and Gregory and Hooke and these other compatriots of Newton, who provided so much of the inspiration and the filigree, as it were, of his works. And Leibniz, so that Newton and Leibniz together provided us with analysis. You know, the Mertonian school and the calculators, after some inspiration, after the Crusades and stuff like that, it had arrived at stuff like analytic and algebraic forms, the formulaic, in terms of variables, in the notation and in the treatment, and vis-a-vis rules or constructions, the geometrical way. And then there's Galileo, so followed some years later, and about this, the arguments of the V viva and the V motrix, that what's won has been the V motrix because it's classical and linear, and very simple in its derivation to so follow that it's correct such usual notions for smooth acceleration for rest in motion is vis-a-vis velocity and displacement. So that is about 1750, almost 1800, the year AD. And then it gets into all the Cavendish school and the Cavendish balance and things going on in that nature quite later. But, you know, with regards to the various establishments of the greater schools, the continental schools, as what resulted more of the industrial ages approach to mechanics, which is very empirical, and then is started to become as of the scientific, where after the Counter-Reformation in the time of Galileo, there was when the church, the Catholic Church, began a sort of rapprochement to establishing that there was a briefer metaphysics providing for science. It's often said as like, well, Galileo suffered persecution at the hands of the Inquisition. It's like, well, that was the system of power, and then it's kind of like it's kind of let out sometimes that the Counter-Reformation was kind of like, well, the Lutherans or the Protestants to the Catholicism ended up having that they then also poo-pooed what was already established as the doctrine and dogma of the doctors of scholasticism after Augustine, Platonism, and theory as of theory. So for science and stuff is a direct descendant and derivative of that. The scientific method, of course, is you can find it in Plato, you can find it in Lucretius, you can find it as carried down for all these ways, till eventually, yet today, we say, well, you know, Karl Popper in the 20th century said we got reproducibility of experiments, observability of experiments, and then for our credo of the scientific method, the falsifiability of experiments. And then we relate that as well directly to our notion of the statistical hypothesis when making a science of things, as of the invalidation of the null hypothesis or the rejection of the null hypothesis, which just goes to show that these are the same common concepts as of all through the thing. And they've been distilled and refined and old wrapped as new again and again to arrive at stuff that's sort of simple to figure out. Though complicated and involved and formulaic and, you know, didactic and all broken out, to make into a linear curriculum so that the whole learnings are derived from the earlier derivations all throughout, vis-a-vis the ability to make models of anything and to have brief working models of anything in so few terms as necessary to convey sufficient detail to faithfully model said theories, that everybody's got their own theory. And then today, as we try to approach how to deal with things like classical mechanics is perfectly suitable for all kinds of things as long as nothing really moves or changes. It's a model of motion and change. And then when it does, then all these things have to get added together. And so for things like, well, how much of an angle do we bank this road so that with how much asphalt and concrete and what kind of aggregate do we engineer this road so that at what kind of speeds and load and traffic and conditions, winter and summer, result that cars stay on the road? Or what kind of grade can we make this road thus that cars stay on the road and it won't fall apart or break the hill? These are the kinds of things that then result in the empirical, where all these matters of load and statics and hydrostatics a lot. That hill up on the mountainside, it's basically a giant puddle at rest, hydrostatics, these kinds of things. That then for figuring out when we have those kind of engineering cases, and you know, if you just at least make it double, then we'll be pretty sure that it will capture the efficient intent of the strength to bear the load with regards to stress and shear and strain or stress and strain, and forces and couplings, and the tensorial products, which establish for all these different directions and dimensions how they go and what they flow and how they are. That classical mechanics is just the most usual sort of thing. And it's the realm of mechanical engineers mostly, who define and derive parts of all sorts, whether it's the clockworks or a fan or anything with regards to machines, compound machines, and the inputs and outputs as open and closed systems. Here in this overall theory of waves as the fungible sort of milieu of the exchange of energy in open systems, exchange and transformation of energy in open systems, the conservation of it, that classical mechanics is very fair and clear. We have what I call kind of Newton's first laws are motion, motion, rest, rest, and equal opposite. And then there's the second law, his third law is basically like, well, we'll just say that's one, and then there's universal gravitation and force equals mass times acceleration. That defines it. And that's great. Really, those second two are one, called F equals ma. And then the force of universal gravitation is its own thing on the side. It's not so much a law of motion, it's a law of gravity. So, but then the whole idea of acceleration and the force involved here is that the force is a function of time. And so it's always got all its implicits. Our explicit is that it's a vector and it's at an instant. It's evaluated at an instant. It's an impulse, it's a classical, it's linear, it's a value. In the implicits, it's a force as a function of time, with all the others, and they're all the function of time. Happily, it's all a function of one time, called the universal time, or the clock hypothesis. Not all have that as so, and many models of physics make it so that when there are any matters of dynamics, then one of the variables in the way that geometry is transformed, not necessarily the geometry that's real, but the geometry of the model, the theoretical model that defines the thing, is that in this manner, time is just another parameter, and so anything that reflects reflection or shear or rotation or slant, either way, is just another reflection in those variables according to the invertibility and reflectability of mathematical variables according to symmetry. So I suppose then symmetry and invariance are kind of the idea of what I've been kind of looking at over the while. In some of the discussions on the discussion boards, there's considerations of dimensional analysis and what's the thing. And so here what that's involved has been this whole idea of the g-forces and force for the model of acceleration, and what with regards to the differences between weight and mass, and with regards to frames, of course, because it's space frames and frame spaces is how our inertial systems so model themselves as open and closed systems, according to the general theory of relativity, which in the classical limit is classical and Newtonian. According to the Lorentz equations, Lorentz invariant, and the Galilean and Lorentz. Usually these days people say, well, now that I've got Lorentz invariant, I'll just kind of leave Galilean invariant right out. And it's like, well, you might want to just kind of leave it in as long as things are going in a straight line. And kind of reserve the Lorentzian then separately as this matter of time and the universal parameter for the Fitzgeraldian and space contraction and the linear and rotational, and the Fitzgerald and the Maxwellian, and for Heaviside. And then as with regards to like Faraday a little bit, but Maxwell and Heaviside. And the Lorentz equations, Lorentz invariance, with regards to stuff like Larmor formula or something like that. Just laying out that with regards to these metrics and norms of these spaces and these coordinate settings of the tensorial products that I'll have to keep folding back together and make conformal mapping, congruency, that there are ways to look at this that both keep valid the previous sorts forms, yet open up to a richer and wider form, while bringing back some of these concepts like a universal clock hypothesis, which goes kind of without saying, and especially so because science, writ large, big science today, has never falsified time reversibility. There are no closed time-like curves, so causality and determinism is still a thing, even in the world of stochastic quantum mechanics. All one theory, it's a continuum mechanics. We model it as stochastic because waves are arbitrarily fast. Yet they're going in a way. You know. So symmetries and invariance are these things, and we'll look at this in terms of groups. So here's a stack of books, and I collected these in my library since some time. I've been studying physics and the mathematical physics, and so this is about group theory in physics, and so then we also get related to the group theory. It helps affect all these things to do with symmetries and reflections. And there's one thing that group theory is missing because it always has inverses, and so you can cancel things out. You know, and the dimensional analysis is like, well, it's over or under equals 1, cancel it out, equals 1. Here's what we've been talking about. It's like, well, it's meters per seconds per meter, meters per second per seconds per meter as integrated over time. It's the walk integral. It's like the path integral, but you know, it goes itself straight, however it goes. That these are the kinds of things that make it so that for the special unitary groups and SU and SO, that these become the very great facilities of the Cartanian for LA Cartan and the geometric algebras and their algebras. And then for the special ordinary and special unitary groups, when we get up to Kaluza-Klein and saying, well, we got 3 dimensions of space, an array or a dimension of time. We're going to call that 3 plus 1 or 3 plus half. And it's Minkowskian space-time. And all what's in it is called uppercase space-time. Everything is inside this continuous manifold or on the continuous manifold. In field theory, we have a field number formalism that everywhere there's the same continuous manifold. It's continuous, and everywhere it's got field number formalisms for any kind of value in any kind of these fields, which are everywhere. All these fields of potential they overlay all together on one thing: electricity, magnetism, the kinetic field, gravity, the fields all live together on this one field. That the higher dimensions are appended to make projective spaces about it. So Kaluza and Klein get up to like, well, let's add another dimension. So in the time when relativity came out, and it was space-time as the new kind of augment to what otherwise is just space in time, it was called the fourth dimension, because basically what that means is anything to do with it which would otherwise be a discontinuity, or to be able to be at 2 places at once, and otherwise a uniform continuous manifold of space. They would have to be one thing together. So the fourth dimension is also uppercase. The fourth dimension is any matter of this perspective and projection. To say abstractly, we can always think of a fourth dimension that is however so you would ever care, or one would ever care to weigh or balance vis-a-vis any other thing. So that was the idea of the concept of the fourth dimension. So with space-time as a formal model, then it has one. So then we have, for Kaluza and Klein, it's like, well, we'll have a fifth dimension. So then with regards to these different fields, and then with their balances and these things, and they come back together, and they got concepts like unitarity, and which is kind of like isotropy, or that everything is kind of the same everywhere, that the laws are the same everywhere, physical laws. That this is a way to get above that stuff and to help relay what it is. So in the geometric algebras, it's kind of a cool thing, because what it does is you have that there's analysis, and then after real analysis, then it gets into complex analysis, because Euler's formula, then the Gaussian analysis made for projections of those in the diagram, relating the complex analysis and the quantities that are real parts to various things that's here called the Eulerian-Gaussian or Gaussian-Eulerian complex analysis. And it's broken down variously in some of these other talks about like the identity dimension and a complex diagram with the anti-commutative or division of the dimensions according to this complex diagram of the identity dimension, which is a plane ray out through all dimensions with all the coordinates the same identity. So anyways, L.A. Cartan, he started a lot more briefly than the whole Eulerian-Gaussian thing with just kind of like the roots of unity and reflections and rotations. And the idea is like, well, with polar coordinates, we can just kind of multiply them or add them together to make a model of rotations as according to these coordinates. So whereas Eulerian and Gaussian kind of trail out that way to make their kind of screw arithmetic that is the same sort of periodic notion that increments. Cartan leaves that as just spinning around. So then beyond the complex numbers, a plus bi, I for the imaginary component, are the quaternions. And so this is William Kingdon Clifford or Clifford numbers, Clifford algebras. And he maybe didn't first invent them, but he came up with them. The idea being he was walking one day to where he was going. And he, instead of just one complex component, there's three. And so there's I, J, and K. And so I, J, and K sort of work like, and forgive me any mistakes from my own, or if I forget, ij equals -1, jk equals -1, and ki equals 1. So they work like complex numbers, except they got, according to a right-hand rule a bit, and then how they multiply together after L.A. Cartan, who he'd been studying, and after Euler and Gauss, who kind of made up their analysis out for these things for the series and what. Then Clifford made for this whole field called Clifford algebras, because the quaternion then made for, instead of using matrix mathematics with its gimbal lock, so that you can take matrices as models of affine transformations, and in 3 dimensions work up a matrix multiplication that works out for the boxes to the boxes, the matrices to matrices. You can multiply a matrix by a rotation and result the coordinates, of an orientation in 3-dimensional space. The quaternions with less components smoothly do that. And they don't have some of the difficulties or problems with regards to the matrix multiplication, which I call gimbal lock, which is basically asymptotes, or what would happen from dividing by 0, the indeterminate quantities, and which usually well enough would just be going around. In the Cartanian and Cliffordian, then they just kind of go around. So then these are objects for the Clifford algebra approach. Because otherwise the physics and up to Kaluza-Klein and Yukawa potentials, and as we get into the potential theory, as we get on up and out into string theory and superstring theory, and why they need all their extra dimensions for what, and using group theory to keep things as about these symmetries, because groups naturally model these. They have identities. They're in the middle. They got inverses. They got an additive inverse that's a multiplicative annihilator too. Or they got, for these natural units, they got the unit, or the dimensionless unit. So these end up being kind of 2 different tracks. One of which is the great stack of matrix mathematics that ends up being able to make for all these kinds of tractable means of echelon and reduction to result elementary formulas, and the products of these Cartanian geometries, objects, that model rotations and otherwise provide for addition formula for what are otherwise these vectors and quantities, and that those make, again, these tensorial products, that it just results like, well, the tensorial products are vectors that add up and keep the same congruencies over these other humps. So as long as they do, that's why a vector is a tensor or whatever by itself. And then we get into tensors because sooner or later there's some bumps and the humps in the coordinate settings, boundaries, and the changes and the barriers. So this group theory ends up being of great utility. And then the idea that there's SU3 is, well, that's 3 dimensions of this group, and then it's got these different symmetries, and so the combinations enumerate into that, like a counting argument makes for counting, and a combinatorial argument makes for combinations. And so then counting gets into like counting to large numbers, and combinatorics gets into combinatorial explosion, so many combinations, permutations, cycles, subsets of these things, which even if it's difficult to figure out what all they are, there's usual algorithms to generate permutations or to estimate the counts of these things, like Stirling's formulas for the factorial or Hadamard's, or the Bernoulli approaches, Pascal, all these different things that come into the binomial and then multinomial, the hypergeometric. I know that's a stack of things, yet they do kind of compose each other and also reflect each other in their outer products of their products and their inner products of their products, which we hope to keep together as all just kind of one course of operators of objects that just all have their usual addition and stay in their own closure of their algebras. That's why it's all kept in linear algebra, or all kept in these Clifford algebras, which have offered some great improvements in some of the means of solutions for these things. And somewhere I have a copy of Hestenes and Sobczyk's book on the classical mechanics rewritten in Clifford algebras. I'll consult that at some later date. It's in the stacks. So group theory in physics, Uki Tang, Michigan State University, United States A, World Scientific, in Singapore. Group theory provides the natural mathematical language to formulate symmetry principles and to derive their consequences in mathematics and in physics. The special functions of mathematical physics, which pervade mathematical analysis, classical physics, and quantum mechanics, invariably originate from underlying symmetries of the problem, although the traditional presentation of subtopics may not expressly emphasize this universal feature. It's largely so because of the invariant theory and the theory of symmetries in conservation law, as with regards here about the dynamics and the running constants and the idea of the stop derivative and these things. Classical mechanics, zeroth laws. Modern developments in all branches of physics are putting more and more emphasis on the role of symmetries of the underlying physical systems. This reduces the order of things and keeps it computed in those symbolically. Thus, the use of group theory has become increasingly important in recent years. This book is written primarily for physicists, Examples on physical applications illustrate advanced group theoretical techniques of a general nature applicable to a wide range of fields such as atomic, nuclear, and particle physics. They include the classification of arbitrary quantum mechanical states and general scattering amplitudes involving particles with spin, Jacob-Wick helicity formalism. So with a Wick rotation, we were reading about that from the path integral, Swanson's path integral. And so that gets into, it's related to that's the Gaussian Eulerian analysis of the screw component. And that's what it is. Multipole moments and radiation for electromagnetic transitions in any physical system. And then the multipole moments, whereas, for example, Feynman's 4-vector, or that in the geometric algebras, those are pretty naturally written up as the inner and outer products, or they have kind of the wedge product as a sort of outer product, and they have various inner and outer products. And then a lot of people will be familiar from linear algebra with a cross product, with a specific principal product that only exists in 3 dimensions and 7. Vis-a-vis that and these other dimensions of analysis of these complex numbers, Cartanian reflections and rotations complex numbers, and Clifford algebras quaternions, and up into the Grassmannians and octonions, that these are particular objects that are very great for use in tensor applications because the model rotation is absent gimbal lock. And there are less things to write. The matroid is kind of like a matrix, and matrix mathematics has usually is defined as particular dimensions, meaning the sizes of dimensions of the lengths of the square or rectangular arrays of matrices that are multiplied together, the products. And so generalized matrices are like, well, you can take any two matrices and multiply them together and you get something, but only part of it's in that middle box. It's got this outer side, it's got this inner side. And then generalized inverses are like, well, what happens when you take those back? It makes all these different things out of whatever it is, but it adds all these different various cases in combinatorial complexity compared to one, that it ends up being a little intractable, if not fungible, and even unsensible. Then there's the matroid. And so the matroid is as of even a higher level concept than the matrix. And I just think of it as a bit more geometric, while still being also linear and adding up, multiplying. At the same time, it's smooth geometrically. Or that if it gets to the various power towers, and that kind of like the tensors is like, it's a higher level concept than things we add together. It's things they add together. Is that matroids is a higher level concept of matrices. It's the matrix, this kind of stuff. When I heard about these things, I looked to study them because they were such advanced mathematics that most people have never heard of them, and if they had very little clue what they were. But then in just so few words, as you've just heard, they can be kind of strung together as one thing. So, Tong, okay, he carries on here a bit. In spite of their clear group theoretical origin and great practical usefulness, these topics are rarely discussed in texts on group theory. Group representation theory is formulated on linear vector spaces. So, and he mentions the finite dimensional, the infinite dimensional. We have Halmos. That's a tough one. When you look to somebody like Giancarlo Rota, and you're like, I got to learn the umbral calculus, which is the methods of finite differences, because there's so many closed forms and forms in that's all kinds of the concrete mathematics and finite differences. You look at Helmholtz, he's like, you know the vector spaces? I got a theory with the infinite dimensional vector space. It's like, great, Helmholtz, thanks. How does that work? He's like, wouldn't you like to know? Right? So this is largely in the finite dimensional and the linear, and full of all these kinds of approaches to then result that the formulas and derivations carry on, that any one given formula fits on a line. Of a sequence of derivations. So the unitary group is special because it ends up that it keeps things back together, like as if you were to try to add together irrational numbers and get back to a rational number. It kind of says it arrives in this manner, and whether space-time is unitary has been a conjecture that has been entertained a lot when it was not really conducive from the derivation that it would be so sensible. It's definitely Machian, though. Yeah, so Yukawa potentials, Clebsch-Gordon, and so kind of like Einstein and Einstein's bridge, and then you get to Clebsch and Clebsch-Gordon. There are some approaches to linearize some things, to reduce the rank or to take something out that's otherwise as of a symmetry, get something in an inner form, make it crunchable, kind of, say, okay, get out and push, then it kind of works in such a manner. Gets into Lorentz spinors. So a spinor or spinor is one of these higher level concepts in the geometric algebras. That also they'll have their own sort of support. Although the mathematics of group theory and the physics of symmetries were not developed simultaneously, as in the case of calculus and mechanics by Newton, the intimate relationship between the two was fully realized and clearly formulated by Wigner and Weil, among others, before 1930. Heaviside was a very sharp guy. So this is one of these books, and it's just about the symmetries in group theory and physics, you know. This started part of the discussion about descriptive differential dynamics. And what it's about is Lie groups, and then methods of symmetries, and then usual approaches to reduce the order of some differential equations, particularly some nonlinear differential equations, to a lower order differential equation that's also ordinary or linear. And when it was read here, the introduction, and there's much to be getting into about that, is the author helped establish that there's a great grab bag toolkit of approaches to dynamical modeling generally, or differential equations and integral equations, is what was so much later discussed in descriptive differential dynamics. That it's so that the symmetry theory generally, and then the Lie groups and the application of the Lie transformation and some like this Buckingham pi and this kind of stuff are very de rigueur these days. Is kind of like, well, everybody would have that usually as part of their course if they're getting into a graduate degree in dynamical modeling or something like that. And there's mentioned Beckland. So Beckland is much later than Sophus Lie. So Sophus Lie and Sillau or whoever it was, and then as of 80 or 100 years before Beckland, Beckland has got a lot of stuff going on, like with the Regi map, the Ricci tensor, and Beckland-Bianchi, as was mentioned about the modern approaches to the soliton and the which is the impulse, trying to extract the principal component of the impulse, is like, which way am I pushing? Of then otherwise these nonlinear things which have a gimbal lock or something, otherwise to find the gradient or otherwise these things, they go together. So, and it gets into the point transformations and infinitesimal generators, because basically the application to make is that it's kind of like, what we're going to do is we're going to make a way that we can express that there's kind of a continuous transformation between this side and the other side, and then it kind of goes over and forward and about and around. And that is the major application that comes out of Lie groups, vis-a-vis the whole theory of symmetry groups and algebra. You can just call it algebra pretty much, vis-a-vis what symmetries of Lie are. That I still need much learning to really understand. ODEs and linear PDEs of first order. And it gets into, like, with this dimensional analysis called the dimensionless analysis, or Buckingham Pi's theorem's results, then the idea is to result a sort of reduction to a linear form, just courtesy that there are only so many dimensional quantities that can kind of so vary, and that they're presumed linear, and then it just results less to crunch. It's like, not only it's linear, but I'm going to be entirely agnostic of the nonlinear, unlinear parts by reducing its order altogether. Which is sensible and very, very tractable. Just not complete, which sometimes is not sensible. Comparing the two differences, commuting generators generate an invariant subgroup. Now, group theory and algebra really has it. There's a lot to be figured for what are the singular aspects and elements of groups. And so when you get into groups in rings and fields, usually it's just directly for the arithmetization, for the numbers they represent. They model each other, the arithmetic usually, and the algebra usually, the groups, rings, and fields. of the integers, rationals, and reals. There's, of course, all the great facility of the finite rings and the prime rings, or ZP, of how they're combinations and permutations, so generate combinations and permutations, and all these concrete aspects of the finite in terms of combinatorial enumeration of the algebra for the discrete things, vis-a-vis the continuous stuff and this kind of stuff. That I'll be looking some more back to group theory of really abstract algebra to find some of these things that help extract whether like the indeterminate forms otherwise. It's like, well, do you have an inverse to the multiplicative annihilator? It's like, well, it's any number you want, but the result is 0 because the multiplicative annihilator takes anything to 0, which also is the multiplicative annihilator. That these are the kinds of things that help result for these indeterminate forms. What happens when there's generalized inverses to default out a product? Oh, one thing. The main idea being to transform the generators to some normal forms, not in their realization in the space of the dependent and independent variables, but in their realization in the space of the first integrals. So he's helping express that there are these kind of threads that remain when it's reduced to a simpler problem. That the things that were complex are what's kind of left out and what's kind of like to try to unravel the knot. That these are kind of the loops or the ends to try to keep track of these things and help build them together. And he talks about the separation of coordinates when there's two symmetries, because that's what goes on this whole field number formalism. It's kind of like, we're just going to put all the fields, their numbers, their formalisms, all in one space. And so any field number, formalism occupied space by its field occupation, formalism, field occupation numbers is any of the field's values according to the forces at that point, at that time, in that space. Well, there's separation of components because they are and aren't independent. They are independent as just kind of a snapshot at the moment, but they are not independent in terms of their sum of histories and sum of potentials evolving together all the time at the same time. This solution can be written in terms of a line integral. By assumption A and the x sub n's are linearly independent, the determinant of the system does not vanish and the derivatives of phi can be computed, and we obtain ... the generalization of the line integral using integrating second order differential equations. Then we get into notions of the contour integral, the line integral, the path integral, and with what path the line integral takes in the contour integral. Largely always about order, rank, reducing it, establishing unknowns in equations of the same order, solving it. Determining lead point symmetries means finding functions, the a to n's of the xi's mu b's and or those epsilons, and a to alpha's xi's mu ub's, such that the symmetry conditions x, matrix x, h sub a equals 0 are satisfied. So that's much like the harmonic theory and the potential and function theory, that there is what that means to be well posed in the sense of Hadamard, what results that entire system solves it suchly in such manners. This is a good insulating mug. It's got a dual wall construction, and air is a pretty natural insulator within it, so it'll keep hot drinks hot or cold drinks cold quite well. Olvers, applications of Lie groups to differential equations. So This series, the graduate text of mathematics by Springer, you'll find these in most university libraries, and they occupy quite a ways in the shelf, where they're scattered all throughout, with their usually identifiable covers and kind of the contents of them being of the series. So largely the contents of this book and the contents of Stefani's book, Differential Equations, their solution using symmetries, would be expected to have much in common. And usually these books are either on the shelf or a professor or grad student has checked them out. Applications covered in the body of the book include calculation of symmetry groups of differential equations, integration of ODEs, including special techniques for Euler-Lagrange equations or Hamiltonian systems, differential invariance and construction of equations with prescribed symmetry groups, group invariant solutions of PDEs, dimensional analysis and the connections between conservation laws and symmetry groups. Generalizations, reasonably self-contained, chosen from classical mechanics, fluid mechanics, elasticity, and other applied areas. Besides the basic theory of manifolds, Lie groups, and algebras, transformation groups, and differential forms, the book delves into more theoretical subjects of prolongation theory and differential equations, the Cauchy-Kovalevskaya theorem, characteristics and integrability of differential equations, extended jet spaces or manifolds, quotient manifolds, adjoint and coadjoint representations of Lie groups, calculus of the variations, and the inverse problem of characterizing those systems, which are Euler-Lagrange equations of some variational problem, differential operators, Euler operators, and variational complex, and the general theory of Poisson structures, both for finite dimensional Hamiltonian systems as well as systems of evolution equations, all of which have direct bearing on the symmetry analysis of differential equations. It's a rather long sentence. I'm impressed. So, much similar content and in various its own directions, helping illustrate that as part of the grab bag toolkit of differential methods, it goes along with others, being sensible, fungible, to help result each other tractable. So I got this the other day, symmetry and integration methods for differential equations. So this is helping to reflect kind of on the other side of all the solutions, the other side of the solutions, the inner and outer products. So let's see kind of what it says here. It's Blumen and Onko's. This book is a significant update of the first 4 chapters of Symmetries and Differential Equations, 1989. By George Blumen and Sukiyaki Kumi. Since 1989, symmetry methods, Sophist Lie, ingenious tricks, solving particular differential equations. Nowadays, it is essential to learn the methods presented in this book to understand existing symbolic manipulation software for obtaining analytical results for differential equations. So this helps illustrate that a large body of work has made a fixture of these applications as numerical methods in the derivations. So their implementation is as after these derivations. And the caveats, what there are, of the conditions, of the expectations, of their correctness, what's called in computer programming defined behavior. There is no undefined behavior. There is only defined behavior. That as with regards to these mathematics and their systems and guarantees and assumptions, as of after any of the unknown implicits, which there are, because it's generally all the mathematical objects, and in relation to science and physics, it's only as good as what that is. The author helps reflect that knowing what these are and how they work explains how these fixtures and systems of the very large scale linear systems that are used to solve all the things do the thing. So it says, thorough treatment of dimensional analysis, well-known dimensionless analysis, which is reduction, compared to this dimensional analysis, like we have to do a fuller and bigger outer product of the dimensional analysis to get that these implicits are not so much the dimensional resonator and dimensionless resonator idea and this dimensional and dimensionless alternator idea are not the same as the dimensionless reduction arguments as after principal component analysis of natural units is what they are. It has its own concept of units and natural units quite well, but the point is that it also has all the implicits, and it's actually the dimensionless is just more and more dimensions stacked on either side that have to stay balanced and stay the same. And also with regards to this walk integral that's always straight, that's its own other kind of a issue that's going on with this mathematical model of the objects in motion for trying to help understand how to solve these multi-body systems of objects in motion as they orbit each other. A reduction algorithm, addition formulas and reduction algorithm, and reductions to addition formula, the great panoply of mathematical analysis and finding solutions. Reducing order through admitted local symmetries and through admitted integrating factors. So integrating factors, I'll have to refresh my understanding of these with regards to the implicits and largely about implicits and parameterization and reparameterization, self-parameterization and reformulation as after implicits and invariance that get involved in these things. Constants, parameters, Noether's theorem, variational, and integrating factors. The linearization operator. So yeah, anytime you see linearization operator, you can generally assume that it means it's a numerical method with an associated error term with regards to that. What it has is that as long as that is bounded so, and either has that it survives the triangle and Cauchy-Schwarz inequality, or that it has a bounded error term and its nonlinear terms don't dominate or blow up, then it should be okay. But it's not an analytic closed form. Linearizations are not closed forms. They're approximations. Hence lemma. Much to it. I'd like to read this some more after reading the more from Gonzalez and Velasquez. This is Gonzalez and Velasquez derivation and the history and the extension and expansion on the Fourier style analysis for its infinite expressions and its numerical methods, which is these infinite expressions are also closed forms and not just approximations. The point being that the Fourier series and Taylor series are proved to be infinite expressions forms. Sort of like Vieta's formula for pi. It's like, well, I take root 2 and I take root 2 of root 2 and plus root 2 over root 2 times root 2 over root 2. Well, that's transcendental. Harmonic function theory. So this is another book from this series. And so if that fellow was published some years before, it's all part of these courses, each one of which is kind of like a class, a 3-credit class in college. Maybe more, maybe less. This gets into, so this is about harmonic theory and function theory. And so we have our functional analysis as we were discussing stuff like the turbulence and this and that. And then we have this whole idea of like, well, the potential theory, as far as the people who study the harmonic functions are concerned, that is their idea of what a potential theory is. It's like, well, why? Well, it kind of makes for waves, and then you have more stuff going on with waves, and with regards to Huygens principle and waves, then it kind of gets up in resonances if they can't really say so. Because some of them are differential geometers. They really don't have that in their model of function, So at some point in time, we just have to leave well enough alone and hope that the linear solver will crunch out the rest of this, or other stopping points, But this book gets into the thing here. Bergman spaces, harmonic functions on half spaces, the Poisson kernel, the Dirichlet problem, the harmonic Hardy spaces. See, a lot of this stuff in terms of the Dirichlet problem and Dirichlet function is addressed with regards to the Fourier style that Dirichlet and Poincare put together. Got a lot going on with regards to algebraic geometry, and the Poincare rough plane and the Dirichlet function that's everywhere discontinuous yet has measure, these kinds of things. Harmonicity at infinity. I think I looked at this one time before. I haven't read this book by page for page, but I've heard of many or most of the things. Boker's theorem. If U is positive harmonic on B minus the empty point, then there's a function V harmonic on B and a constant B greater than or equal to 0 such that U of x equals, if n equals 2, it equals Vx plus B log 1 over quantity absolute value x. And if n is greater than 2, then Vx plus B times the absolute value of x to the 2 minus n. So that 2 to the 2 minus n gets into the whole idea of the differential geometry and the Laplacians and the whole central organization of Laplacians in terms of harmonic theory about the second partials in either direction being 0, and then according to the quadrature that being absolute 0, and vis-a-vis cusps and saddles and saddle horns and these kinds of things with regard from topology that make for why that there's things like trying to find which way it's going, because that's the way, and that's what's down, trying to figure that out. Harmonicity at infinity, here we go. Because the Kelvin transform preserves harmonicity, we make the following definition. If E is a subset of Rn is compact and U is harmonic on Rn / E, so for a surface removed, a subspace of Rn, then U is harmonic at infinity, provided Kelvin transform U has a removable singularity at the origin. So this kind of reflects on the differential forms and the singular forms and all this kinds of stuff, and it helps reflect that things like the algebra and the quotients and the notion of whether it's division or multiplication first, and whether a ring or a field is as if after having a field is addition and multiplication, or it's really the inverse in the increment and the inverse of division. That these are the kinds of things that help illustrate the same kind of concept, can then be sort of readily applied to what's singular in an indeterminate form in this higher level of multidimensional analysis of the harmonics and harmonicity at infinity. That for things like the singular integral in the convolutional setting at infinity, and its inverse close to 0 or at 0, and these kinds of things, that it helps to establish to reflect that there's really only one kind of this singularity to figure out first in the one-dimensional case, and it's about point inversion and 0 and infinity and 1. They become even just central. It helps a lot when those are primary and elementary and first in the theory, the identity expression constants. I first wrote those in an expression 25 or 30 years ago. I was like, this is 1 over infinity equals 0. And everybody's like, yeah, everybody knows 1 over infinity equals 0. The limit of 1 over infinity, n as n goes infinity is 0. I'm like, what I mean is these are 3 constants. And one equals 0 times infinity. That it would be involved then, because that's just a reflection on this deconstructive arithmetic and algebra. So many years later, it's the same theory. I'm lucky I have the same theory throughout. It just kind of goes around. So I wanted to look at these books and talk some more about classical mechanics and mechanics of motion and motion. But what I got into a lot was group theory, algebra. ideas of how it sort of relates these mathematical models, the physical models, dimensional modeling of the dynamical modeling and dynamical analysis. Well, I shall so hope you have a great day, and that you know I hope it's that it's the summertime in the northern hemisphere. So according to global warming, it's just been getting real hot, and I can operate basically between like negative 40 degrees to about 120 degrees. But ever since they adjusted the thermometers upwards some 10 years ago, so what used to be like, 105 or 110 degrees now just reads off as like 90 or 95 degrees, and this kind of the real temperature, or what you might want to put as it. That I do better at 40 below, which is metric or imperial, than 140 above. But not to be inhospitable. Well, I shall so hope you have a great day.